In this chapter, I'll cover some performance optimizations, and it's important to review these as you first design your scene graph and start adding interaction capability to your application. Perhaps the most important one is to first focus on how you're organizing the scene graph. And this is critical because Hoops is, again, a graphical database. It's traversing the segments and the contents of the segments, both the geometry and looking at the attributes. And that segment structure will have a significant impact on performance. There is some CPU side overhead on every update to walk through the scene graph and draw it out to the display. So the overarching guideline is to try to minimize the number of segments to the greatest extent possible, and also to minimize the amount of graphical or geometric primitives. So Hoops is designed, Visualize is designed for the scene graph to be organized based on attributes. So ideally, group items based on similar graphical information. And when we talk about using the minimum number of graphical primitives, not only does that mean use the most appropriate graphical primitive. For example, you would use a Hoops shell, a group of facets to represent a part in an assembly. But there's also some other primitives that could be appropriate and effective, such as polycylinders. And a classic example there would be if we have a mechanical CAD assembly. Frequently there's one geometric or BREP body for each part, and then there can be a BREP face for each kind of group of triangles in a part. So let's say we have a cylinder that could be represented as a single shell instead of three separate shells, one for the top, one for the bottom, and one for the side of the cylindrical part of that item. In this slide, I'd like to highlight a few attributes that can influence performance. One would be culling, which has a few sub-options, and I'll highlight two of them in particular. A very common one that most people are familiar with is backface or backplane culling. So if there is a polygon handedness set first in the scene graph on the segments of interest, then Hoops Visualize has a concept of what is the front and back of polygons. And turning on backface culling will instruct Hoops to not draw polygons or facets that are facing away from the camera in a view-dependent time. Also, extent culling is a pretty important option to consider. And what that will do is instruct Visualize to cull away items whose area in screen space is smaller than the specified amount. So for example, you might have a large model with a lot of small parts in it, and as you zoom further out or interact with the scene in orbit, culling away these small items could significantly boost performance and not really have much of a visual impact on the scene. And transparency has some settings which can also influence performance. I would encourage people to review both the transparency algorithm and method. The algorithm influences how we handle transparent geometry in terms of its accuracy. The default would be something called depth peeling, where we sort of peel away the surfaces to expose what's behind it, and that works by looking at a value of a number of layers that are set. Default is layer 1, meaning we'll draw make a single pass at the transparent geometry in the scene. And if you wanted something a little more accurate, let's say you had 3 overlapping sets of transparent geometry, you would have to peel away multiple layers. So to get an accurate result in this case, we'd have to set depth peeling layer equal 3 to have the proper blending of the 3 overlapping items. So all transparent geometry has to get drawn once with each layer that's peeled away. And we do recommend using the depth peeling algorithm with 1 layer. We can see an example of some of these in action. Here we have a fairly large assembly. I have no performance optimizations enabled right now. We're redrawing everything on every update. If I set our extent culling to, let's say, 30 pixels, all items whose length of one of their screen space bounding boxes is that size or smaller will be culled away. And as you can see, the performance is significantly improved. Okay. Another option we could experiment with here is the transparency layers. Right now we have it set to 1, so we're using depth peeling. We're making a single pass on each update of the transparent geometry. So that would mean that if I had 2 overlapping transparent items, like over on the right side here, we wouldn't have a fully accurate result. Let's say a transparent front panel and transparent back panels. If I set layer to 2, then we'll make 2 passes of that geometry to get proper blending. And of course, if I had 3 overlapping layers and wanted full accurate transparency, I could set it to 3. Not much of a performance impact on this model because the amount of transparent geometry in here relative to the total amount of geometry is fairly small. Might not look like it because there's a lot of large transparent panels, but there's a tremendous amount of other parts inside this assembly.